Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Our today's topic is medical imaging. So, let us consider that what is dealt with in the medical imaging. It is basically, it considers non-invasive or semi-invasive visualization of internal organs, tissues, etc. Not only their anatomy, but also their functioning. And usually imaging are in the form of 2-dimension or in 3-dimension, and also there are medical images for videos. So there are major modalities of this imaging, which in fact we will be discussing very briefly in this lecture. They are projection X-ray or usual X-ray, what we consider, that is the radiography. Then X-ray computed tomography or CT scan images. Also there are nuclear medicine images, which are also a kind of tomography, that is emission tomography. And there are two modalities that we will be considering here. One is SPECT and another one is PET, that is single photon emission computed tomography and positron emission tomography. And then magnetic resonance imaging and ultrasound. There are other modalities of medical imaging also, but these are the few modalities which we will be considering in this particular lecture. So, let us first consider the X-ray imaging methodology. Now, this X-ray imaging system, X-ray images or X-rays are discovered by Wilhelm Conrad Röntgen in 1895 in Würzburg, Germany. And because of this discovery, he got the inaugural Nobel Prize in 1901. So, the mechanism for generation of X-ray, as you can see here, that there is a tube. It's like the cathode ray tube, but from the cathode ray, when we get the beams of electron, those electrons are hitting the anode here with a very high speed in between, and before touching the actual, before getting absorbed, and they are hitting at a very high speed, and also depending upon the material of this particular surface which makes this anode, it is generating X-rays. It is actually a obstruction, so it is not the charged one. So it just strikes the respective atoms of the material, and from the atoms, so there are atomic interactions, subatomic interaction of subatomic particles through which X-rays are generated. We will also get a brief glimpse of the kind of phenomena what is happening there. And with this, I am also showing you a kind of historical image of a historical X-ray tube, very early X-ray tube, vacuum X-ray tube, what we had in the early stages of its development. And this is another historic image. It is the first X-ray image captured by Wilhelm Röntgen, and it is the left hand of his wife Anna Berthel Ludwig. So it was, as you can see, it was presented to Professor Ludwig Gender of the Physics Institute, University of Freiburg in 1st January 1896. So that is the first X-ray image, and where you can see that the bones of the fingers, those are their structures are perceptible through this image. So let us try to understand how this imaging takes place for using the X-ray, using X-rays. So X-ray, they are projected, or they are rather transmitted through an object, and then the transmitted ray it hits the respective detectors, and from the detectors, it basically the intensity of the transmitted ray that is being detected as an image pixel. And as you can see that in this case, it is like the rays are considered as a parallel, so it's a case of parallel projection. So when you have the image of the object on the image plane, which is shown by this array IDXY, so it's a kind of parallel projection of the object on that plane, and since it transmits through the object, so any internal structure, it will have its effect on that production of this image. So it records the transmission of X-rays through the object, and it's basically an electromagnetic wave with the wavelength between 0.1 to 10 nanometer, and there is a particular physical law by which this energy source gets transmitted through the medium, and it follows a law, Lambert-Beer's law, which was proposed and which was observed much before the discovery of X-ray. So it is in this law, according to this law, the radiation intensity while transmission, it decreases in proportion to the product of intensity and the distance travelled by the ray. So it can be expressed mathematically in this way, as you can see that the change of intensity, that is shown as here delta I, is proportional to the intensity of the respective ray and also the distance travelled, which is considered here delta Z. So we are showing as if this direction of travelling is the Z axis and these are X and Y axis. So with following this kind of convention, we have written Z here, and there is a proportionality constant which depends upon the property of the material through which it is getting transmitted, or medium. So this coefficient or this parameter, what actually distinguishes characterizes the point of transmissions or the median when it produces the respective X-ray image. So you can from this from this relationship, we can derive that actually you can express the intensity of the transmitted ray is related to in this form, that is, this is the initial intensity before the travelling of the distance I naught, which is the intensity of the source, and then when it travels through the medium, you can see it is exponentially decaying this particular intensity, and this is the kind of integrations over this length Z. So mu x z, it is called X-ray attenuation coefficient, as I was mentioning, this mu, and it's a function of the respective tissue what is there, because it is passing through the body. So depending upon the tissue properties, this attenuation coefficient varies, and because of that only you get variation in the images, and we understand different kind of structures of tissues by relating with them. It's also a function of electron density, which means the production of the X-ray electron density and atomic number. That means which is the respective the interaction with the X-ray with the atoms within the body. Those are in the subatomic level. Those interactions determine also this particular physical parameter mu. And you should note that this integration is a line integral over the distance. So, this we should note, because we will see that it has its tremendous use when we are considering the tomographic reconstruction of images. So, when we talk about projection X-ray imaging in the case of medical application, we found that the diagnostic X-ray band it lies between these two. I have already mentioned that the wavelength is between 0.1 nanometer to 0.1 nanometer to 10 nanometer. So this is the energy level. So we assume the speed of light in the vacuum. So this is the energy level that should, that is on which it is X-ray is operating for the diagnostic cases. Because it requires interactions of X-ray photons with object and it works in a specific energy band. If it is above this band, then it would be too transparent, which means almost it is not variation over that line integral will not be much there. So you cannot observe the internal structure because of that every point will behave almost similar. It will just transmit the energy. And if it is below this band, once again, then it would be too dark, which means the intensity will not reach the detector. So again, no, you will not observe those variations of those structures. So that's why it should be within this band. So and well below this band would be wavelengths are too long. So that is also another problem. So it would be I mean there's the same operation. Now let us consider the physics behind emission of X-ray. As we have seen in the basic X-ray tube, that it is the electron beams which are hitting a material surface and then the beams are produced. So it is the interaction of electrons with the atoms on the surface, and in the atoms there are nucleus and also there are electrons revolving around this atom. So two different processes by which these X-rays are emitted. One through interactions with an inertial electron, and another one is interaction with the nucleus. So this picture tries to tell you about these interactions. As you can see that this is the kind of interactions over the because of the attraction of nucleus and also the effect of the electrons. So X-ray while passing through this particular rather electron beams passing through this through the inner shell of the nucleus and also presence of inner shell of the atom and also presence of nucleus, it would deviate its path and it would lose photon energy. But this is a very this energy is not so strong. Relative intensity is high, is low. We call this kind of phenomena as Bremsstrahlung, which means this slows down the speed of the electron, and the radiated energy is also of low intensity value. But when it hits directly an electron, the electron hitting the electron, that causes a kind of quantum jump, because what happens then, this electron gets deflected. So it basically ejects the electron from this inner shell to outside the atom, and this electron also, by losing energy, it will also deviate from its path, but it will also go out from the system. So what happens then, this atom becomes an ion. So because the electron is ejected, so it would be a positive, first thing it would be a positive atom, positive ion, and then because the inertial electron is ejected, so there would be an hole created in the inner shell, and which makes an outer shell electron to move inner shell. And as you know that outer shell electron is of higher energy, so while moving actually it will emit energy. So it will emit, it will radiate, it will basically emit photons, and those photons are of higher intensity values, and they produces this kind of characteristic radiation. So this is in fact this is the radiation which is primarily used for diagnostic X-rays. So when it is an interaction with the inertial electron, this characteristic X-ray radiation produced, and it is sufficiently strong to ionize the target atom by removing the inertial electron. And as I mentioned, the electron from outer shell an electron from outer shell will move in the inner shell, and that causes the X-ray emission. Whereas when it interacts with nucleus, and so the colliding electrons slowed down and deviated, and it, loss in kinetic energy reappears as an X-ray photon. But there the amount of energy of that photon is much lower than what is being emitted due to the interaction with the inner shell electron. On the other hand, if I consider the absorption of X-ray, there are three kinds of absorption, and here it means that now X-ray is passing through the body, which means again X-ray is passing through an atom, and then the energy of the X-ray, it gets absorbed in through various interactions. So one interaction is that if the energy is very high, it would behave differently with atomic electrons. So you can see that there are different kinds of scattering takes place because of high energy interaction with electron atoms. So one is that it takes care of photoelectric absorption, because the X-ray, when it excites an electron in the inner shell, then this energy is absorbed, and because it is getting higher energy, this electron will be ejected. So that is what is photoelectric absorption. That is one kind of emission. Then also you have again this Compton scattering, and in Compton scattering it is partially this energy is absorbed. It is here it is fully absorbed, so no radiation takes place, only electron gets ejected. So in that way there is no X-ray radiation transmitted. But in Compton scattering, as you can see, the electron gets ejected and this X-ray energy gets attenuated, but it still gets transmitted along its path. So this is the transmission. This is what this transmission takes place, and this is the major phenomena which contributes to the diagnostic imaging through X-ray. So this is about the high energy interaction. If it is very high energy absorptions by nucleons, then what happens in nucleus? There are two particles which are emitted from the nucleons. One is electron, another is positron. So there is a pair production, but no, here it is not very much relevant to diagnostic X-ray. As you can see that you are not getting X-ray out of this process. And then low energy absorption, it just simply it's a Rayleigh scattering which is harmful for patients, and it is not used in the diagnostic X-ray. So in Rayleigh scattering, X-ray simply goes through the shells and they gets deviated, and also it loses certain energy. So just to give you a bit more details, elaborations of this phenomena, let us once again summarize the key points, key highlights of those absorption phenomena. Like in photoelectric absorption, it gives off complete energy to eject an electron, creating a positive ion, and then it creates a hole in the inner shell, and then emission of photon due to movement of an electron from an outer shell to inner shell. So photoelectric absorption also emits X-ray, but that X-ray is because of the emission of photon due to movement of an electron from an outer shell. But as you can see that the path of the emission is not very directed in this case, because in imaging you require also the path gets directed towards your detector, and it follows the principle of parallel projections, or whatever it should be. It should follow the line of propagation in the same direction. So then your projection becomes useful for the purpose of imaging. When you are considering Compton scattering, in Compton scattering, this X-ray has considerable higher energy than the binding energy of electron. So in that case, this electron absorbs partially those energy and it gets ejected. and you produce an ion. On the other end also, the X-ray also, it loses energy, but it just with attenuated energy, it could be by an angle 0 to 180 degrees. So it gets some deflection. So it is not exactly parallel, but it gets some deflection. But this is the major phenomena what happens in our body. And then the Rayleigh scattering, as I mentioned, that in this case, this energy is considerably lower than the binding energy of electron. So electron just absorbs the energy and it may move from its inner shell to outer shell if it is sufficiently energy, but otherwise it will simply vibrate. And this vibration also it can be transferred by a proton to any arbitrary angle, and no ion is created. So one example of radiographic image which has been shown here.